first edition of the book that, is recommended for this class. And it was lost in my house fire. And I was able to find another first edition, and it was rearranged and made into a sculpture by my sled dog. I have a bunch of other editions, and one now, thanks also to the sled dog, is in pieces. So you'll start to see me with pages, like individual pages of the textbook. It's very convenient this way, especially since, I can do that now. So I've got an example to work that's kind of like number 3 in the homework. And yet this is, all right, so. Okay, so this question has all of the aspects of this kind of a problem that we need or that we should know. So I would say my best first step, I know what my final properties are, so I know I can figure out how much cold work I want in the very last step in order to get those properties. So if you still have your homework or this image of strength and ductility versus percent cold work, then for brass, I want 450 megapascals. That looks to me to be about 40% cold work. 450 megapascals yield strength. Percent cold work has to be greater than or equal to 40%. Got that from the graph. I want 13% ductility. So that looks to me like pretty close to 30% cold work. So that means that the percent cold work has to be less than or equal to 30%. Wait, that's getting impossible. Brass, 13, 30%. String, 50, 40%. Okay, I know they didn't intend for this to be an impossible problem. So I'm going to make an adjustment here. 30%. Okay, so let's make that be, I see, this is really gradual, but I'm going to make my requirements for strength, I'm going to make them be, it's great that you might be that I just didn't read this graph. 400. So let's make it be so we'll say yeah, let's make that 350. And for 350 percent cold work has to be greater than about 20. You see why I couldn't do it before. And it could be that I'm just reading the graph incorrectly, because it's really close. So those are my criteria. Now I know in the very final step that I should have something between 20 and 30% cold work. Now if I want the fewest number of steps, then I'm going to maximize on that cold work. If you were solving this problem on a test, and I wrote it just like this, you could pick anything between 20 and 30. So I'm just interjecting one possible thought. And that is, I kind of want to maximize cold work because maybe I'll have to do it in fewer steps. So I'm going to choose 30% cold work. Again, this is a choice. This isn't something to remember or do. I'm going to choose 30% cold work. So if I do that, then if my final diameter is, what did they say, 12.7 millimeters, then what would my initial diameter be? With 30% cold work. And if it's a round stock, then we know the percent cold work is going to be the final diameter squared minus the original diameter squared over the original diameter squared. No, other way around. Okay. Original diameter is bigger. There we go. So I want 30%, 0.30, to be equal to, I don't know this original diameter. I do know the final over the original. So I'm doing some rearranging there. And I have that 0.7 times the original diameter squared will be equal to 12.7 squared. Okay, so that is so the original diameter squared is 230 millimeters squared. Take the square root of that. I get 15.2. Which is smaller than I have to start with. So I'm going to have to do this in steps. Olivia.
Why is it 0.7?
So this is 0.3 d0 squared is equal to d0 squared minus 12.7 squared. So I take this is essentially 1 minus 0.3 is 0.7. Okay, so because this diameter is smaller than 19 millimeters, this process has to be conducted in more than one step. Okay, so my final product has a diameter of 12.2 millimeters. It has yield strength of greater than or equal to 350. And it has ductility greater than equal to 13% elongation. And we now know that to get there with 30% cold work, I need to start with 15.2. Doesn't really matter what my properties are, but I know I need to start with 15.2 without any cold work. So the step before that is annealing. So that this is 0% cold work. Annealing will get rid of all the cold work, the effects of the cold work. So I do that annealing after I've gotten down to 15.2 millimeters. Now maybe I can just do this in 2 steps. So if I go, can I go from 19 millimeters and 35% cold work to 15.2 millimeters without exceeding 65% cold work. So I'm starting with 35% cold work and a certain dimension. Can I continue to cold work that sample, get to 15.2, and not be over 65% cold work? Because if I'm over 65% cold work, it will crack. So, let's see, D original, 19 squared minus D final, 15.2 squared over original. What's that?
0.36.
What is it?
0.36.
It's only 36%. Except, add that to the 35% I already have, and I've exceeded my 65. So I'm close, and at this point, there's all, you can choose anything. We just need this percent cold work to not be more than 30. Right? We do know that we'll only need one more step. We're very close. So what I would do then is I would say, okay, well, this step then, how much cold work do I want to use? Well, really, anything less than 30. Let's go 25. Now, this again is one of those kind of multiple right answer problems. I'm just choosing 25 because I really kind of don't want to choose 30. It seems like I'm getting close to breaking, but I want as much as I can, so I get this done. You can choose anything between 0 and 30. I'm going to choose 25% cold work. Okay. So if I have 25% cold work and I'm ending up with 15.2 millimeters, then this dimension, so I don't want to put these in order. So the first thing we did was this. So I'm going to call this step 1. 2, and step 3. And that was all of this. And then step 4. Can I do that? No, I can't. Okay. Step 5. Choose percent called work that's less than 30%. So that means I'm going to choose 25%. So D original, that's the thing we don't know. D final is 15.2 over D original should be equal to 0.25. So that says that 0.75 D0 squared is 15.2 squared. So that's 17.6. Okay, so we have 17.6 millimeters. And that's going to give me, I want to start here with no cold work. So I'm going to have to anneal, because I'm going to have 17.6 millimeters with 35 plus 25, or 60% cold work. Right? That would be this. Did I just do something twice?
Yeah, I was gonna say, is it 20, how do you know it's 25?
I just chose 25.
No,
That's,
from the original.
yeah, I don't.
Could you just anneal it at the very beginning of the process? And then do the one that we did? That
We
was
could,
36?
yeah. So what Alice suggests is, hey, let's just get it back to 0% cold work before we do anything. And then we could do it in 2 steps, and that would be correct. Or you could do some cold work and anneal, more 25% cold work, anneal, the last amount of cold work, which was 30% cold work. So let me finish with that, and then I'll put this as an alert. So I go here, and this is where I have 0. No, I've annealed it to get 0. This is where I have 25 plus 35, 60. Cold work. Right. And then anneal it. And then starting with getting lost in the middle of this problem. 15. 30% cold work, get final. And you know, so there's a final. It's existing no. I want to see this through. If I'm going to have to do another step, then I don't have this. And then this. And then this is going to have some percent cold work. There we go. And we start with 19 millimeters. So for this last bit, and this would be step 6. I have original 19 minus 17.6, these are squared, over 19 squared, and that's equal to 14% cooler. So this is going to be here. That started at 35. All right. So this is starting from the back, moving to the front, making sure that I don't exceed 65% cold work total, making sure I anneal before I have cold work at each step. So there's cold work there, anneal beforehand, cold work here, anneal beforehand, cold work here. So that's one possible solution, okay? Following sort of the same steps all the way back. Now, Ella suggested, good thought, is once we realized that this was too much cold work with my existing 35%, and we had to add another step, it would suggest that maybe instead, this is another correct answer, or anneal first, and remove 35% more. And now I have 19 millimeters, no cold work. And I can do what we were going to do here. I can go to 15.2 millimeters using 36% cold work. Then anneal. Then 30% cold work. To final 12.2 millimeters with 30%, right? Now, which one would you pick? Well, kind of depends on how much it costs to run your ovens. Because doing the cold work isn't a lot of energy typically, but the furnace might be. Let's see. So we really start with 19 millimeters, 35% cold work, and an anneal. So here we've got 2 anneals, there we've got 2 anneals. I don't see why it would be better not to do this. I think it would be better to do this. Okay? But either is the correct answer. All right? Any questions? Okay, there's one other that was in here that I thought,
I guess in the first way we did it, that 25% is just a guess now, because we annealed it beforehand.
yeah,
Okay.
yep, right. I mean, and we could iterate.
Because we could have pushed it all the way up to say
30.
55%, right?
Well, true, yeah, you could have,
We annealed it beforehand, maybe.
right,
Got rid of a few steps.
there you go.
Okay.
Very good point. So Tim's point is, hey, if I can do 55, 60% cold work, why don't I do that here? But I can't do it with my original, no matter what, because that's too much. If I'm going to anneal here, yeah, I don't know that there's any advantage to increasing this number. Because you want this as your final number. All right, so here's one other where you use that table, or that, I'm sorry, those graphs. It says, it is necessary to choose a metal alloy that will, for an application that requires yield strength at least 345 megapascals and ductility of at least 20%. If the alloy is to be cold worked, which of these metals can be used? Copper, brass, 1040 steel. So in this case, all we need to do is look at these curves for each metal and see if it's possible to have both a ductility of 20% and a strength of 345. All right, so for 1040, to get that strength of 345, I don't need, no cold work is necessary to have the yield strength greater than 345. All right, that's fine. And what about ductility? Can I get 20% ductility with steel? Yeah. As long as I don't have any more, it's 20%. as long as I don't have any more than maybe 4 or 3. %, elongation is possible. As long as percent over is less than 4%. Okay, so I could use 1040. What about brass? If I want a yield strength of at least 345 megapascals with brass, how much cold work do I need? L.
Sorry, I'm checking.
That's good.
About like 15%?
15
Yeah. For brass, right?
for brass. I think I needed more than that, but again, this is the want of a straight edge.
It's
345. I think I need more like 20.
I think it's close, it's like in between 15 and 20.
Yeah. Who votes for 20? Or who votes for 15?
I'd say like 17.
17? Okay. So for brass, 17% cold work will give strength of 345. Okay. Can I get a ductility of 20% with 17% cold work or more? Or maybe if you want to answer this the same way we've been doing the others, if I want 20% cold work, 20% elongation on the brass, what's my maximum percent cold work from the graph? Anybody? Tim, can you tell me?
It's like 24%.
That looks like about right. So I can get, as long as percent cold work doesn't exceed 24%. What was it? 20% elongation is possible. All right. So I can use brass, I can use steel. What about copper? How much cold work do I need to get 345 megapascals yield strength for copper?
Like 55% over.
Like 65?
I said 55, but somewhere like pretty high.
It's very high, yeah. Like it's barely getting above that. So maybe we could say, have to have 60% cold work or more. 60% cold work is the minimum amount to get yield strength of 345. To get 20% elongation, ductility on copper, how much, how much cold work can I do? Somebody other than Ella and Tim, anybody other than Ella and Tim? Yes,
Colder has to be less than 15%.
that's about right. So in order to get 20% elongation, I have to have less than 15% cold work. So copper can't be used because I can't get both the strength I want and the ductility. Steel can be used, but having that small amount of cold work is kind of tight, but a good use. Brass seems somewhat ideal. It's a nice big wind. All right, but both brass and steel could be used. Okay, any questions? Those are all the different kinds of questions with that topic. All right, let's take a 5-minute break, and then we'll start up with the next topic. 2 planes of atoms. And I can't control the size of the atoms or their weight. What could I maybe control that would make it easier for them to slide past one another?
Maybe you could like excite those atoms with heat.
What's that?
You could excite the atoms with heat.
Right. I'm thinking much more basic than that. If I've got 2 objects, flat objects that I want to be able to move past one another, and I want to reduce their friction, and I can't change their weight, I guess I suppose this is in the real world, would it be like if I could make a hover craft instead of something on the ground? So what I'm trying to get to is the distance between the planes. The bigger that distance, the easier it would be for them to move past one another. So increase the distance between the planes. Okay, so these atoms, depending on the packing, in some directions they're right next to one another. In some directions they're not right next to one another, it's a space. And when I do this motion, I'm going to be doing that motion one spacing at a time. The atom is going to move from one place to the next place as it's moving in that direction. And so the closer the atoms are to one another, the easier it would be for those atoms to relocate. If I'm going to slide my plane in this direction with a parallel to the board, it's a shorter distance incrementally to move the plane. If I'm moving it back and forth, I got to have enough energy to move the atom further from where it is, because these are all these atoms are shifting one spot. Okay, so the factor that would make the easiest direction would be where the atoms are closest together. Okay. So, let's think about BCC versus FCC. We'll do that first. Actually, before we do that, we're going to do something, just one little thing from a topic called crystallography. And crystallography is just about describing where planes and directions are in a crystal. So describing planes. In a cubic system. After we describe planes, we'll describe directions. So if I have a cubic system where every unit cell is cube, there are three planes, there are three plane types that we have to know about. The first type of plane are the faces of the cube. Now, how many unique non-parallel faces are there on a cube? Non-parallel. 3. Front and back, top and the bottom, left and the right. Right? So there's 3 types of faces. Each of them has what's called a Miller index to describe it. So Miller indices, rather than derive this, I think it's easiest if I just give it to you. So the Miller indices look like this, and then I'll show you which one's which. So, here's X, here's Y, here's Z, always true for materials. The 1, 0, 0 plane crosses X, where there's a 1. And it's parallel to Y and Z. Let me just add here that I'm not going to make you reproduce this, but I do want you to understand it. That's the reason I'm going through it. All right, so if I want to talk about the planes that are parallel to Y and Z, and that are perpendicular to X, well, that would be the front and the back, right? Front and the back are parallel to Z and Y, and they're perpendicular to X. Okay, which of these is the top and bottom? You know, this represents the front and the back. Which of these represent the top and the bottom?
The last one.
Right, because it's perpendicular to Z, parallel to X and Y. and this would be the left and right, right? There's three types. We call this the family, fancy bracket, family 100. Three planes, 100, 0, 1, 0, 0, 0, 1. Now notice there's no commas with no indices, and we use regular parentheses. Okay, that's the first group of planes. The second group of planes are the planes that look like this. So there's that one, and then there's one perpendicular to it there, right? And then there's this one. And it's perpendicular. Like that. Okay, so this one, let's see. This one would cross in the x direction, and it would cross in the y direction, but it's parallel to z. So there's a 1 where there's an x, there's 1 where there's a y, there's a 0 where there's a z. And it's perpendicular has a dot product, and I'm not sure how far you are in the math sequence, of 0. It has a 1 and a 1 and a 0, but either of these ones is negative. Now let me just add here, this is a plane. I could also write it as -1, -1, 0. They're equivalent. This one I could write as +1, -1, 0. There's two perpendicular planes that are parallel to Z. See that? So this plane, and it's perpendicular, what direction is it parallel to? the Y. So it's parallel to Y. So that means there's a 0 in the Y location. And it crosses let's see, if I put my origin here, it crosses at X and it crosses at C. So these, that's how it's drawn. It won't be important to me that you can draw these, I just want to illustrate them. So there's that one, and it's perpendicular. You just make either of these negative. By convention, I guess, or habit, I always just make the first one negative. Okay? So there's two perpendicular planes that are parallel to Z. There's two perpendicular planes that are parallel to Y. And then that's parallel to X. Yeah? So that is the 0, 1, 1, and the 0, negative 1, 1. So there were 3 different planes in the first family. There's 6 different planes in the second family. The third family are not parallel to any axis. They cross X, Y, and Z axes. So they look like this. That's one of them. That is 1, 1, 1. How many planes are like that in the cube? More than 2. Easiest way of imagining this is this, of course, is a triangle. Top is here. You can rotate it. There could be a top here, here, or there. And so they have indices where the X is negative, the Y is negative, and the Z is negative. Those are the 4 unique 1, 1, 1 planes. Okay? Now, if for whatever reason I don't want 1 bar 1, 1, I could instead have 1, 1 bar, 1 bar. That's the exact negative. But I can't have them both. So these two are the same. Negatives of one another, it's basically looking at the plane from this side or coming around and looking at the plane from the other side. So those are the planes on which that we need to look at for dislocation motion in PCC and FCC. All right, what about the directions? The first group of directions are the ones that are the edges of the cube. Now, there's 4 of these are all parallel. So they're not unique, but there's this one, and there's that one. Those are the 3 unique directions. And just like with planes, they have indices, and we use bars for directions. 1, 0, 0, and 0, 1, 0, and 0, 0, 1. All right, and just so you know, the 1, 0, 0 is going in the positive X. The 0, 1, 0 is going in the positive Y. 0, 0, 1 going in the positive Z. That's where they're located. Let me add here, just like this, the family. 110 has members 110. And then here, these are the numbers. Of the 1 family. Members, family, okay. All right, so back over here at directions. For talking about a family of directions, we use these greater than, lesser than brackets. Those are the 3 unique directions. Now, parallel to them, but just with the head of the arrow at the other end, would be 1 bar, 0, 0, and 0, 1 bar, 1, and so on. They're not unique. They just are positive or negative to one another. Okay, so that's one of the families. And one thing to note, for example, 1, 0, 0 direction is perpendicular to the 1, 0, 0 plane. Also, the direction X, Y, Z lies in plane A, B, C if A times X plus B times Y plus C times Z is equal to 0. So these these are like identities. What's for crystallography? Okay, so that's the first family. Second family, you can imagine this follows a pattern here. These are going to be the directions that are perpendicular to planes like that. So they're called the face diagonals. These are cube edges. These are called face diagonals. And it doesn't matter which end the head of the arrow is on. Just try to illustrate these. So these two that are on the sides, so over the sides over here. No, that's a family. These two that are on the sides, this is moving in X and Z. So these are moving on the X, Z plane. And they're perpendicular to Y. So being perpendicular to Y, they have 0 where the Y index goes, and a 1 for the X and Z. They move in. There are two that are in the XY plane. They're perpendicular to Z. So they would be 1, 1, 0, and 1 bar, 1, 0. And then the third are on the front and the back. And they are perpendicular to X. So they are 0, 1, 1, and 0, -1, 1 bar. 1. Again, I'm not going to make a picture with a cube and put a direction and say, what is that direction? But we are going to be using these different indices. I kind of want you to know where they are. So the family of directions 1, 0, 0 has these 3 directions. The family of directions that are face diagonals have 6 members. there's one other family. And that's the family that are full body diagonals. Family 111, which includes one bar, one bar, and one bar. What is it called, this one? Somewhat easy to see. And just so you know, if I put the head up there, this is 1 in the x, -1, and the y, 1 in z. That's the indices for that direction. And there's 4 of them. Okay, why all of this? I need to identify which planes are furthest apart from one another, and which directions have the atoms closest together. All right, so I'm writing this here. You don't have to go back to the page. I just want to refer back to this for FCC. We've got atoms at the corners and the center of each face, right? So that is the sorry, 101. Plane. That's what the atoms look like on that plane. On a plane in the family 10, parallel to x, z. There we go. The family planes of planes 1, 1, 0, they look like that. So I have atom, atom, atom. That's what that plane looks like. With me so far? And the other family of planes So looking at those 3 planes, and knowing that the planes that are most densely packed are the furthest from one another. This is also an identity. So for FCC, the planes that are most densely packed are in this family. So that means that that family are the slit planes for FCC. No, that's not right. Actually, it doesn't really look like it. But these are the most closely packed for FCC. Yeah. 110. All right, for BCC, what do these look like? Let's see, I used red. Uh, 100 plane. It's the face. Looks like that. And for the blue. 110 plane. Looks like that. And the 111 plane. You know, I was right before. I was right before. Sorry. This is. And then, so for BCC, that's what the 111 looks like. So for BCC, most densely packed. Is the family 110. Okay, so the slip planes for for BCC are in the family 110.
Professor, would the, 111 plane, the triangle, would it cut through the body?
Has to cut through the center to count.
Right. Okay.
And it wouldn't cross through the center because it goes through the center of the sides.
Right. Okay.
That's a good question. You kind of want to put it there, but we only count those atoms that it passes through the center of. Okay, so let's see. These planes are 1, 1, 1, 1 bar, 1, 1, 1, 1 bar, 1, and 1, 1, 1 bar. Okay, looking at these, the direction that's most highly packed are the ones where the atoms are touching. Here, and they're touching here. So the most densely packed plane are the type 111, the most densely packed directions are the phase diagonals. One, 1, 0. Okay. So let's look at these planes like this. Each of these directions is one of those highly packed directions, right? You see that? On that plane, there's 3 highly packed directions. And the directions, I kind of want to just tell you rather than prove. This plane is one of them, right? And it's got one direction that's parallel to X. And it's got one direction that's parallel to Z, and it's got one direction that's parallel to Y. So I'm just going to write the directions for each of these planes down rather than prove it. You don't need to memorize it, but you'll notice when we start looking at that thing I passed out where the numbers come from. On this plane, I'm going to have one direction that's parallel to X, one that's parallel to Y, and one that's parallel to Z. And in order to be, every direction that's in a plane has to have that dot product, AX plus BY plus CZ equal to 0. So one of these will have to be negative in each case. So those are the 3 directions that are on that plane. And again, it's just supports that table that I'm giving you, where all that stuff comes from. And so there's 3 directions in each of these. There's 4 planes, FCC, 4 planes, 3 directions on each plane. So that's 12 ways that could deform. For BCC, this is the plane where deformation happens, and it happens in one of these 2 directions. So the planes are each, there are 2 directions. So for BCC, there are 6 planes, 2 directions for each plane. Systems. So, look at that thing I just handed you, that page I just handed you. The first column is the plane, the second column is the direction. You'll see, on one side, the first 3 planes are the same, and then the next 3, and then so on. So there's 1, 2, 3, 4 different planes, 3 directions on each. So this side is FCC. The one that has 1, 1, 1 in the plane column. If you look at the other side, in my case, it's 2 different pages. The plane column is 1, 1, 0 type, and there's 6 of them. It's 1, 2, 3, 4, 5, 6 planes, and on each plane, 2 directions. So this side, with 1, 1, 0 in the first column, that's for BCC. And we'll start there with stuff that actually matters all week from today. Okay? No class Friday. All right.